Welcome back to another class on speech processing. So last class I was talking about how the idea of deep neural network, right, is going to be applied in speech recognition problem. So there is still what's called a hybrid approach, because we are going to use the deep neural network to give some kind of a posterior, and I'll revise or just repeat it a couple of minutes what we discussed last class. But the HMM part, the hidden Markov part, continues to be available. Okay, so hidden Markov model comes from more classical statistical kind of things, and the deep learning is replacing the GMM part. So it's a mix of both the neural net deep learning kind of approaches and a little bit of statistical framework from HMMs. Therefore, these are called hybrid models. Okay, so if you remember last class where I was where I ended is the fact that I have a waveform. From the waveform I extract every 25 milliseconds these MEL filter bank features, right, and the deep neural network is going to take these MEL filter bank, and during training I need to know which particular sound it belongs to, right. I am going to use the neural network to be trained in such a way that given a MEL filter bank feature, it will predict what sound is at the phoneme is coming at the output. So therefore, I need to know for every frame what was the corresponding phoneme. Okay, and that is called alignment problem. Okay, so in this hybrid approach, we need alignment. Even in the GMM HMM, we are going to need alignment. Okay, we need the alignment to know for each sound, or sorry, for each MEL filter bank feature every 25 milliseconds, what was the corresponding sound in the speech signal, what is the corresponding phoneme in the speech signal. And the whole idea here is we are going to find out the phoneme sequence, right. We are going to find out the sequence of phonemes, because you are getting a sequence of vectors. For each vector you are going to find out what phoneme it corresponds to. Okay, and that is going to be an issue, or is not an, there can we do a better thing is what we want to check on, right. So okay, so let me revise what we did last class, and you might recollect what I did last class a little bit. And if you recall, the whole idea of training so we are going to replace the GMM with the deep neural network, and the deep neural network is trained such that it will output the posterior of a particular basically given. So let me just explain a little more in detail. So I am given a waveform, right. So this is a waveform that is given, and every 25 millisecond, that is green is one segment of 25 millisecond, red is another segment of 25 millisecond, black is another segment of 25 millisecond. How did I arrive at 25 millisecond? Historically, a lot of people have worked on it and found out 25 is a good number. Okay, from each one of these I am going to extract a MEL filter bank features. Okay, and if I had only extracted one MEL filter bank feature, what would I do? I would take that as an input, and if I know for that MEL filter bank, the green MEL filter bank, I know that the corresponding sound is, let us say, what did I assume here? Ah. Okay, if I assume the sound is ah, then I take that vector, feed it. Now it's a vector, right. So the input will be having, this will be the input layer. We'll take this 80 dimensional vector or inputs, then this is the hidden layer, right. So this is the hidden layer, and then at the output we have to recognize one of the 45 or 50 phonemes. Let us say we are identifying 45 phonemes. So this will be a 45 class problem. Okay, the output layer will be having a softmax, and this is the target. What is the target? What is my desired output, right? So for the sound particular 25 milliseconds, I know the sound is ah. So only that guy will become 1. With a probability 1, I am doing that because I am going to use softmax. All the others should have probability 0. Okay. Then the next red MEL filter bank feature comes. Then I feed through this neural network. Now I know that, let us say by alignment, I know that the red corresponds to sound okay. So therefore, again it will pass through the neural network, and then now I know the target should be right. So and okay, so is coming. The third will be corresponding to the sound d. Okay. But in practice what is going to happen is I am going to get the waveform, I am going to get these MFCC vectors every 25 milliseconds, I am going to pass through the same network, right, and so at the output for each of these vectors I am going to get a target vector, right, where one of them, whichever sound is the correct sound, will be 1 and all the others will be 0. Similarly, for the second vector I have to set a target where all will be 0 except for one particular sound, whichever is the sound I have, T3 and so on. So, this is called alignment because I need supervision. So, for every input I need to know what was the correct output, right, correct desired target, right. So, this is called supervision, also known as alignment, right. So, we need to align. So, for every feature I need to know the sound class or phoneme, that means I need to know the target. So, for every MEL filter bank OI I need to know the corresponding TI. So, every if I have O1, O2, let us say O73, I need to know while training the corresponding T1, T2 all the way up to T73, right. And each of this will be an 80 dimensional vector. These are MEL filter bank features. And these are your targets, right. So, this will be 46 cross 1 or something if I have 45 phonemes plus silence also one phoneme, right. So, the target will be one of these 46 sounds. So, each one of these are going to be 46 dimensional vectors, right. So, this is called the alignment. Okay. Now, how do I get alignment in practice, right? So, it is not easy for a human to listen to it and say this is E and all. So, what we do is, how do we get alignment? So, to get alignment what I do is, there are two ways to do it. One is called flat start, uniformly segment the data. I have discussed this idea long time back in when I have talked about GMM, HMM. The other way is to use some prior related model. Okay. So, some prior related model and use that to do what is called forced alignment, right. What is forced alignment? So, I have the waveform and from that I get the MFCC vectors, okay, somewhere O something, O capital T. Then I have corresponding text in words. This is passed through a lexicon. Then we get sequence of phonemes. Okay, and it uses the model to align the O vectors with the phonemes. So, this is called forced alignment. Okay. And generally this is not a very forced alignment. I mean, alignments are not perfect. Okay. So, it depends on the quality of the model and also so at least boundaries are not correctly got, and this you can also see the difficulty. Example, in handwriting cursive handwriting this is, okay. So, that is very important. So, if I write something like, now if I ask you where does one letter end, not easy to identify. Correct. So, for example, here, do you know where S ended and A started? Not very clear, right? So, the same thing, the boundaries are very difficult, because I am like cursive writing, this is continuous spoken speech, right. So, there is no clear boundaries, right. So, therefore, this becomes, and one is this, second is because we are doing frame by frame decision. Okay. What do I mean by that? Every frame we are trying to assign to a particular phoneme. Okay. This, but in reality, what am I interested in? I am only interested in correctly getting the sequence of sounds, sequence of phonemes, and from that use a lexicon to get the words, and therefore sequence of sequence of words to form a sentence. But actual speech recognition problem, what is the idea in actual speech recognition? So, given the waveform and given the sequence of vectors O2, O3 and so on, O capital T, to get the correct sequence of phonemes. So, to get the correct sequence of phonemes, not the more difficult problem of getting correctly every frame assigned to the corresponding phoneme, right. Correct. So, actually there is a simpler problem with that. We are actually trying to solve a simpler problem, but we are trying to force a lot more. So, if I draw it, it will be very clear. So, what we are saying is that you have these inputs, and you have these hidden layers, right. So, you have these hidden layers, there could be multiple of them, right. So, it is a deep network, so you have multiple of them, right. So, you have all of this, right. So, you have multiple of them, right, and then you have some outputs here. So, this is your phonemes sequence. So, what happens is every vector in the original problem, every vector O1, if you want O1, O2, O3, O4, these vectors, if I feed like a sequence, right, O1 we want to correctly get correct, matching T1, T2, we are trying to match this, right. Right. So, here we every mistake is going to affect. So, every error is important and captured at frame level. But my problem is much more simpler, right? So, I don't correctly identify. So, for example, let us say it is yes, okay. So, if I get here a a yes, right. So, this is the correct target, let us say. But if I did a sir, this is going to be marked as error, right. So, this is an error, correct. This is target and output is this guy, right. So, output is this guy. So, I am going to be marking this guy as error, right. Or or I might have y e h s. Again, this is going to be marked as error, right. Another case, another output, okay. But that is because at the boundary sometimes y can be, we ourselves saw that it's not going to be perfect, right. So, where do I say yes sends and so in my mind I made a decision that this should be y and that should be y. I mean, the alignment model has told me that this should be y, this should be y. It could itself make mistakes, and these errors are going to be saying that this is an error. Oh, be careful, like that, you should make sure that I correctly estimate this, okay. On the other hand, the simpler problem is I don't care, if I get correct sequence of sounds. So, if I get if I get y e h s or y e h s, all of these are equally correct, right. Because I know that this basically I am going to, what am I going to do? I am going to see these consecutive guys and say that anyway the unique guys are going to be E S S. So, this is Y E H S, right. So, consecutive frames. So, this is O1, O2, O3, O4, right. So, this is the thing, right. So, it does not matter if I make some mistakes, but the sequence still continues to be correctly identified, right. And from that I can always use a lexicon to get the word, right. So, this is the basic idea of connectionist temporal classification. So, so this is the basic idea of connectionist temporal classification or CTC, okay. This was proposed by a person called Alex Graves, and his PhD advisor is Schmidhuber, okay. We will see that Schmidhuber has done many important contributions. So, this actually if you like some just like history, this was actually in 2006 we had Ichkai in Hyderabad, okay. Actually, the first idea of CTC, Alex Graves proposed it here, right. Coincidentally, it was a conference that was held in India itself, and but it did not catch on until about, I would say, 2012 or around that time, where he published another paper with Hinton, and then it caught on, and you may hear about it if you are at least in speech processing. You will hear a lot about this, okay. And then it did not take off for various reasons. But now, in 2012-13 it was important. Then there's something called transducers that we introduced. But again, now it has found a lot of attention, right? It's quite extensively used nowadays. So, Alex Graves' idea was very simple, exactly what I said. Why? What is the problem in speech recognition? You have to get the correct sequence of phonemes, right? That is the whole objective. So, why are you worried that every frame I should correctly identify, and that too, the targets themselves may be making some errors, the alignments themselves may be wrong. So why are we so worried about? So in the process, if because you are saying it's wrong, the network has to really make an effort to make sure every frame is correctly mapping the target. Okay, we need a much more lenient or less stringent objective function. So basic idea is only the sequence is important, right? Okay, so this is the basic idea of CTC. So we need to get only the correct sequence of phonemes at the output. Okay, so this is the new objective function. The old objective function was what? So he has changed the objective, right? Remember, we need some kind of error measurement. We need to know, right, what error we are making, and then we back propagate, right? So if the error, our criteria is that you should not make error at every frame correctly whatever is the target you should get at the output. That is a very strict condition, right? So if y is here and y is here and y is there and it estimates as you are going to say it's wrong, okay, and is identified as y, you are going to say it's wrong. But remember, these alignment boundaries are not perfect, right? So we are going to make quite a few errors there, right? So why are we so obsessed about all of these guys? Instead, why not just worry that I need to get the sequence correctly, which is a less stringent condition and more easy to meet, and therefore the network will train better and faster, and probably will even train will give better performance, right? So that is the whole idea of CTC.